Tonight's presentation is titled When Metal Lets Us Down. And our presenter is Mike Bush. Mike is president of Savvy Aircraft Maintenance Management. Mike is an author for numerous aviation publications. He holds a Certified Flight Instructor's Certificate, A&P Mechanics Certificate with the Inspection Authorization, and in 2008 he was the Aviation Maintenance Technician of the Year, honored by the FAA, and he's also a member of EAA. Mike, thanks so much for being with us again tonight. I'm going to turn control of the presentation over to you.
Well, thanks, Tim. Good evening. Good evening, everybody. As Tim said, the title of tonight's presentation is When Metal Lets Us Down, and we're going to be talking primarily about the subject of metal fatigue, a subject that sometimes has fairly spectacular consequences in aviation. I imagine most of you may recognize this pretty famous picture from, what was it, 1988. This was the Aloha pop-top airplane that had a massive fatigue failure in flight, and a big piece of the cabin departed the airplane, got a lot of attention. This was a pretty bad one, but this is not, it was not an isolated case. Here's a Southwest, I think it's a 737 that had a similar failure, and here are some investigators taking a close look at where the cabin top skin failed. You can see it just sort of ripped away at a row of rivets up there. Getting down towards the low end of the aviation food chain where most of us hang out, here's a Lycoming cylinder that had a fatigue failure of the head to barrel junction, and the cylinder head separated from the barrel in flight, something that can really get your attention when it happens to you in flight. That one's a Lycoming. Here's a Continental engine that had a head to barrel separation. This is the most common kind of head to barrel separation, where the head departs the barrel, but there's enough stuff connecting the head that it doesn't depart the premises altogether. It just separates from the barrel by a half, 3/4 of an inch, shuts down the cylinder, and you wind up making a forced landing somewhere and changing your underwear. Here's another head to barrel separation. I think this one is also a Continental engine. I think this was an ECI cylinder that failed, and again, the cylinder head was held captive by a bunch of the stuff that's connected to it, but it separated a fair amount from the cylinder and shut the cylinder down. Getting a little close to home, this is a photograph of a cylinder head from one of my engines that suffered a fatigue crack between the top spark plug hole and the fuel injector hole, a fairly common place for Continental cylinders to crack. And the pink tinge is from where we applied dye penetrant, and the blue line in the crack is actually fuel stains. The fuel filled the crack because the crack extended into the fuel injector hole, and that's what that blue stuff is. But anyway, the head was cracked, and it's pretty obvious crack because of the blue fuel stain highlighting it. Here's a similar crack on another cylinder that's viewed from the inside of the cylinder. I believe this was a borescope image, and you can see a pretty nasty fatigue crack in the cylinder head emanating from the exhaust valve seat area and growing towards the top spark plug hole. This one looks pretty expensive. This is one of the nastier crankcase cracks that I've seen. I've seen a lot of crankcase cracks, but this one's pretty bad. This was on a Lycoming engine, obviously, and the pink color again is from dye penetrant that was sprayed on the surface of the crankcase in order to make the crack more apparent. But that's a pretty good sized crack. That looks like it was probably a 3 or 4 inch long crack. So that engine definitely is not going to be flying for a while. This photo is a little bit hard to see, but what it is it's a propeller blade, and you can see that it has a real nasty nick on the leading edge in the upper left-hand corner, and that nick was not detected and dressed out at pre-flight, and so it served as a stress riser and the initiation point for a fatigue crack that looks like it's progressing across the blade pretty significantly, and that the tip of that propeller blade would have departed the premises if that had gone for very much longer, and that can really get your attention. Oh, this one is sort of amazing. This is a Cessna 185 landing gear that suffered a fatigue failure right through that massive, beefy spring steel landing gear, that Whitman gear that Cessna uses. It's pretty amazing to see a hunk of metal that beefy, big giant piece of steel, fatigue fracture all the way through. Here's what the end of that fracture looked like, and it turned out that this was a fracture that originated at an area of corrosion, which served as a stress riser. We'll talk about stress risers in a little bit, and progressed through the part until the crack grew to the point that the spring failed in overload, probably on a moderately hard landing. But anyway, those are some examples of the kinds of fatigue failures that we face in aviation. So we're going to do a little bit of discussion about metallurgy and talk a little bit about how this stuff happens and what we can do about it and so on. And so let's start with some really basic stuff. I want to talk about the concept of stress and strain. When you take a piece of metal and you apply a force to it, the metal deforms. And the more force you apply to it, the more the metal deforms. And we call the force that we apply stress. And we call the amount that the amount that the metal deforms in response to that stress is called strain. So those are two really important terms that we use when we're discussing this stuff: stress and strain. Stress is the force, strain is the reaction to the force. It's the amount of deformation that the metal has in response to that amount of stress. And there's a basic thing called Hooke's law that says that strain is proportional to stress. So if we put twice as much force on a piece of metal, it should deform twice as much. And that's expressed in that kind of fancy looking formula that says delta L, that's the change in the length of the piece of metal, is equal to the force we apply to it, divided by a fudge factor called Young's modulus, or the modulus of elasticity, which is a measure of, for the particular material that we're working with, how much it deforms per unit of stress applied to it. So in theory, the metal's reaction to force is, the deformation is a linear function of how much force we apply to it. But it turns out that that's only true if the force that we apply to the metal is fairly small. For real materials, stress is proportional to strain only if the stress is small enough that it doesn't start to destroy the metal. And in order to dig down a little bit into that concept, I'll need to introduce a couple of more terms. deformation of metal can be either elastic or plastic. Metal starts out as elastic. What elastic means is you put a force on it, the metal deforms. When you take the force away, the metal goes back to the way it was before. Deformation that reverses itself when the force is removed is called elastic deformation. So, if you're flying along in a airliner and you go through some turbulence and you see the aluminum wing structure bend in response to the turbulence, it returns to its original shape, and that's elastic deformation. But if we put enough force on a piece of metal, and we strain it beyond what's called its elastic limit or its yield point, then the metal becomes plastic and the deformation is permanent. When you take the force away, the metal doesn't go back to its original shape. It stays in the deformed shape. So if we apply relatively small forces to metal, the metal deforms elastically in a reversible fashion. If we apply a large enough force to the metal, then it deforms in a plastic fashion. It becomes permanently deformed. And then if we deform it plastically enough and get it to beyond what's called its ultimate strength, then it actually breaks. It actually breaks in two. And we can visualize this with a diagram. This diagram is showing the force, the stress that we're placing on the metal on the y-axis, on the vertical axis, and the strain, that is the amount that the metal deforms or elongates in response to that stress, along the horizontal of the x-axis. And you can see that when we start applying force, the strain increases linearly up to what's called the proportional limit. And at that point, when we apply more force, the metal starts breaking down and it starts to deform plastically. And then if we apply enough force that it reaches its ultimate strength, then the metal actually ruptures. It actually breaks in two. Now, if you think about it, this behavior that I just described, the fact that metal deforms elastically when you apply a relatively small force to it and deforms plastically or permanently when you apply enough force to it, is exactly what makes metal behave like metal as opposed to other substances. You can think about various other substances that don't behave like that. For example, rubber is almost solely elastic. It always returns back to the way it was. You can't really deform rubber and make it stay deformed unless you heat it up. Glass, similarly, if you apply a force to glass, it will deform in an elastic fashion, and if you apply enough force, it will rupture, but it never really gets into a plastic state unless, again, it's heated. If we want to form glass plastically, we have to put it in a furnace and heat it up and play glassblower. Similarly, if we consider materials like clay or putty, those are almost entirely plastic. When we deform them, they stay deformed. They don't ever go back to the way they were. But metal has this kind of unique property that under small forces, it is elastic, and under large forces, it's plastic. And that's a big part of what makes metal useful. We can form it and shape it by applying large forces to it, and then it will retain that shape when we apply relatively small forces to it. And that's exactly what makes metal so useful, is that particular characteristic that it starts out elastic, and then under enough force becomes plastic. So we want metal to be plastic when we're building an airplane, but we really don't want it to be plastic when we're flying an airplane. We don't want to put enough force on it to permanently deform it in general. Now we can put force on materials in various ways. The force can be in compression or in tension or in shear. When we talk about metal fatigue, we're normally thinking about force applied in tension, force that is trying to tear the material apart, if you will. You normally do not have a fatigue problem when metal is loaded in compression. Now, there are other ways of loading metal besides these three. For example, bending. Bending is actually a kind of a complicated combination of stressing metal in compression and stressing metal in tension. Different parts of the material are loaded in tension or compression when we bend metal. The same thing is true when we apply a torque type load to metal. Some of it is compression and some of it is in tension. But it's where the metal is in tension that we worry about fatigue happening. Another important thing to keep in mind when we put a load on metal is that the stress that we apply to the metal is almost never uniformly distributed through the metal. For example, for parts that are subject to bending loads or torsional loads, almost all of the stress is at the surface of the part, and very little of the stress is on the inside of the part. And in fact, that's one of the reasons that in building aircraft, we frequently use hollow parts like tubing, because a tube is almost as strong and will take almost as much stress as a solid part of the same dimension, because it is the surface where all of the stress is concentrated, and the interior of the part is very lightly loaded, and therefore we can save a lot of weight simply by making the interior part go away, since it really isn't adding very much to the strength of the part. Now, if we load a part to the point that it fails, a solid part tends to fail a little less spectacularly than a hollow part does. But as long as the loads on the part are within the design limits, so that we aren't loading the part to its yield point, a hollow part like a tube is literally as strong as its solid counterpart, and so we tend to use hollow things because they save a lot of weight. Similarly, in aircraft, we frequently use beams, things like I-beams and C-beams for spars and other structural elements, and almost all of the stress on an I-beam or a C-beam is handled by the caps on the top and the bottom of the beam. One of those caps is loaded in tension, and one of those caps is loaded in compression when we're putting a bending moment on the beam. And the web that connects the two caps has very little stress on it. And that's why frequently when we design an I-beam or a C-beam, the web is drilled out with lots of lightning holes because it doesn't have to be very strong. It really doesn't bear very much of the stress. The web is simply there to hold the two caps in position, but the heavy lifting, if you will, are done by the caps on the top and bottom, and the web is very lightly loaded. let's talk about stress risers. We've been talking about the fact that stress is not evenly concentrated. It tends to be concentrated to the outside of parts, tends to be concentrated in the caps on beam type structures. But also stress is concentrated at and magnified by any geometric discontinuities in the part. Things like corners, holes, notches, threads, scratches, nicks, corrosion pits, anything like that will cause a concentration of the stress. And that's why in heavily loaded parts, we want them to be very smooth. The most heavily loaded parts normally are polished to a very smooth surface to eliminate the stress risers that would be created by any surface pits. We have to be very, very careful about drilling holes in heavily loaded parts because those holes will cause a very large magnification of stress around the hole. And we have to be very careful about things like corner radiuses and that sort of thing, because any sharp geometric discontinuity, corners, threads, things like that, cause a great local increase in stress and tend to be where cracks and metal fatigue starts. We'll talk a little bit about metal fatigue. Sort of the classic example is you take a paper clip and you bend it back and forth, and if you bend it back and forth enough, it breaks in two. And that's kind of the classic metal fatigue. And what you're actually doing when you're bending that paper clip back and forth is you're putting stress on the structure of the metal. Metal is actually a lattice of atoms in a crystalline form, and they're held together with atomic bonds. And by bending that clip back and forth, what you're doing is eventually starting to rupture those bonds between the atoms that make up the crystal lattice. We'll take a closer look at what the crystals look like in a minute, but that's basically the concept. We can cause a part to fail in a couple of different ways. A static failure is simply caused by putting the part in overload and loading it to the point that it ruptures. We can do low cycle fatigue, which is basically what we're doing with the paper clip, where we're doing small local plastic deformations. The paper clip is made out of a very soft, malleable metal. Paper clips, when you bend them, they stay bent. They typically don't spring back unless you bend them with very, very small amount of force. So when we bend a paper clip back and forth between our fingers, we're deforming it plastically, and which means that we're actually destroying those atomic bonds, and so it doesn't take a whole lot of cycles back and forth before that paper clip breaks. On the other hand, if we deform metal while it's in its elastic range, which is what we normally do in an airplane, say a propeller blade or a wing spar or that sort of thing, so we're staying within the elastic range of the metal and not permanently deforming it. It takes a very much larger number of repetitive stress cycles before the metal will start to develop a fatigue crack. And that's the kind of failure mode we mostly see in aircraft. Occasionally, we'll see failures caused by a part being loaded beyond its design limit and going plastic on us. But most of the time, we're dealing with parts that are operated within their design limits, but are simply repetitively stressed enough times that a fatigue crack begins. And there's there's something called an SN curve, which talks about the relationship between how much force we put on that metal, how much stress we put on it, and how many repetitive stress cycles it will take before the part fails. And you can sort of see from the curve if we put very high forces on a piece of metal, it doesn't take an awful lot of cycles before the metal will start to fail. But if we put a lower stress on it, it will take a lot more cycles before the metal fails. And the smaller the stress we put on the metal, the more cycles of stress it can withstand before it starts to develop a fatigue fracture. Now, some kinds of metal have what's known as a fatigue limit. And a fatigue limit is a very important concept. It says that fatigue limit is kind of, if you will, the minimum level of stress that is capable of causing the metal to fatigue. And if repetitive stress is applied to the metal that's below the fatigue limit, then it can absorb an infinite number of repetitive stress cycles without ever developing cracks. And it turns out that not all metals have this characteristic. In particular, ferrous metals, like iron and steel, have fatigue limits. And if they are operated with stress levels below their fatigue limit, they have effectively an infinite fatigue life. They will never develop fatigue problems. So, for example, the crankshaft in your engine undergoes an awful lot of repetitive stress cycles, but it is designed to be operated so that the stress on it is below the fatigue limit of the steel. And therefore, a crankshaft should have an infinite fatigue life. It should never, ever fail in fatigue. Now, actually, there been some studies done. There was a study done by Lycoming that indicated that the typical life of a crankshaft, as long as it's not exposed to some catastrophic event like a prop strike and it's not allowed to rust, the useful life of a crankshaft is something like 14,000 hours, which is, 7 TBOs or something. And when a crankshaft is ultimately taken out of service after 14,000 hours, it's normally because it has worn beyond acceptable limits, but it's almost never because it has developed any sort of fatigue problems, because the crankshaft is operated below its fatigue limit, and so it really doesn't feel the repetitive stress unless it for some reason is operated above its fatigue limit. For example, a prop strike or a violent pre-ignition event or something that stresses the crankshaft beyond the level of stress that it's really designed to handle. Then, of course, it could develop fatigue problems, and that's why after a prop strike, we always have to do a whole bunch of non-destructive testing on the crankshaft to see whether it has developed any cracking. But under normal conditions, something like a crankshaft will never crack because it's made of ferrous metal, made of steel, and it is designed to operate below its fatigue limit. On the other hand, non-ferrous metals like aluminum and magnesium and so on, and we have a lot of non-ferrous metals in our airplanes, particularly aluminum, they do not have a fatigue limit. Or you could say the fatigue limit is 0. So that means that no matter how small the stress is that you put on an aluminum part, eventually, if you stress it enough times, it will fail in fatigue. It's not a question of if, it's a question of when. Non-ferrous metal parts always will fail in fatigue if they're subject to enough stress cycles. Now, the smaller the stress, the more cycles they can withstand before they start to crack. but they always will reach a point of cracking. Whereas a steel part, if you operate it at a low enough stress, it can go forever. Why do ferrous metals and non-ferrous metals behave differently in this respect? Well, that's the subject for a very long discussion of metallurgy, which is probably way above my pay grade. But the short answer is that the crystalline structure of ferrous metals and non-ferrous metals are different. The ferrous metals like iron and steel have what is called a bodied centered cubic crystalline structure, where you have atoms at the corners of a cube and another atom in the center of that cube. Whereas non-ferrous metals like aluminum have what is called a face-centered cubic structure, where there are atoms in the center of each of the square faces, each of the 6 square faces of the cube, rather than an atom in the center of the cube. And the face-centered structure packs a lot more atoms into a given amount of space, and is much less able to withstand deformation without tearing apart some of those bonds. Whereas the body-centered structure that ferrous metals have can withstand a fair amount of deformation and then spring back elastically because the bonds haven't been broken. So that's the short answer as to why ferrous metals and non-ferrous metals behave differently in this regard, and why the ferrous metals have a fatigue limit, a non-zero fatigue limit, but non-ferrous metals don't. In general, body-centered cubic metals like iron and steel are harder and less malleable, and face-centered cubic structure metals like aluminum or copper or any of the precious metals, or all FCC kind of structures, are softer, they're less hard, they're more malleable, and they are more susceptible to fatigue failure. So as we said, with ferrous metals, if subject to repetitive stress below the fatigue limit, they can theoretically remain in service forever, unless they corrode or are worn beyond service limits or undergo some catastrophic event that causes them to be stressed above their fatigue limit, like a prop strike, for example. Whereas non-ferrous metals, no matter how low the stress level, they will eventually crack and fail if subject to enough stress cycles. So particularly with non-ferrous metals, we have to worry about the frequency of the repetitive stress. And some parts of an airplane, let's say wing spars, the frequency of the stress cycles is so low that the predicted fatigue life of those parts, even though it is finite, is very, very long. And I mean, for example, we have single-engine Cessnas with aluminum wing spars that have been in service for 40 and 50,000 hours without any fatigue cracking problem on the wing spars. But the wing spars, the frequency at which wing spars are repetitively stressed is very, very low. But there are other parts in our airplanes, particularly things that have to do with the engine and propeller, that go through millions of repetitive stress cycles. And for those, fatigue life may be quite significant, and it's not uncommon to see some of those parts fail in fatigue, as some of the pictures that I showed you at the beginning of this session illustrate. Let's talk a little bit about the subject of torque and preload, and this is a subject that I really could easily devote an entire webinar to, and probably should do so at some time in the future. But we have a lot of fasteners, or a lot of threaded fasteners in our aircraft and in our engines. That where we rotate a nut on some threads to apply a force to the fastener. That force is called preload. And by tightening the nut, or tightening the head of a bolt in some cases, what we're actually doing, we're creating a force on the fastener, that's stress, and in response, the fastener is actually stretching. That's the strain part. And we are using a torque wrench to apply enough force to cause that fastener to stretch enough to create a joint that will hold together firmly under whatever forces are applied to it. The classic case, and the one that we frequently run into lots of problems with, is this one, is the case where we have cylinders that are bolted to a crankcase, typically with 8 hold-down fasteners, and we have 8 nuts that we have to torque down when we're installing a cylinder, and we have to torque them down with quite a lot of force in order to create a joint that will hold firm, even though the cylinder is going through quite a lot of stress when the engine is running. Now let's quantify that a little bit. I'll just use some round numbers that are kind of in the ballpark. During each combustion event in a typical piston aircraft engine, the force on the cylinder that's trying to rip it away from the crankcase is on the order of 100,000 pounds. And we typically have 8 threaded fasteners on each cylinder base flange that are holding that cylinder base flange attached to the crankcase. So when the cylinder undergoes a peak force of 100,000 pounds, each one of those 8 fasteners, if the load were perfectly equally distributed across the 8, which is not really quite true, but each one of those fasteners would be subject to a peak stress each combustion cycle of about 13,000 pounds. Now, here's where the torquing and the preload come in. If each of those hold-down fasteners is torqued to establish a preload, or a stretch, if you will, on that fastener, that is greater than the maximum force trying to tear that joint apart. So say each fastener is preloaded to 15 or 20,000 pounds. Then the combustion events cannot cause the joint to move at all. That joint will be perfectly stationary in the face of that 100,000 pound combustion event. The fasteners will not stretch any more than the static amount that they were stretched when the cylinder was installed and the fasteners were torqued down. And so effectively those fasteners don't even feel the combustion event, if you will, because they already have a greater preload than the maximum force being applied to pulling that joint apart. But on the other hand, if the hold-down fasteners weren't torqued to something over 13,000 pounds, let's say they were only torqued to 10,000 pounds, then every time a combustion event happened, that cylinder base flange would pull ever so slightly away from the crankcase. Probably not even enough to measure. We're talking about a fraction of a thousandth of an inch. But each time that happened, each of those hold-down fasteners would feel a repetitive stress cycle. And because those things over time will be exposed to millions of these events that fastener will eventually fail in fatigue, and if enough of them fail the cylinder, will depart the aircraft. So it's absolutely critical for high stress fasteners like cylinder hold down nuts, crankcase through bolts, the rod bolts that hold the cap onto the big end of the connecting rod, probably the most highly stressed fastener in an engine. All of those very highly stressed fasteners, it is absolutely ultra critical that the torque be correct. The torque has to be applied sufficiently so that the fastener has enough preload to exceed the maximum operating stress that will be placed on that fastener during engine operation. It can't be torqued so much that it causes the fastener to reach its yield point, because then the fastener will come apart and overload. So there's this window of where the torque has to be. It has to be larger than the maximum operating stress on the fastener, and it has to be smaller than the yield point of the fastener. The torquing instructions have to be followed to the letter to make sure that those fasteners are preloaded to exactly the right range in order for both of those conditions to be met. Here are some examples that, and we see this with alarming frequency, of what happens when, for some reason, the proper preload is not applied to these critical fasteners. Here's a cylinder hold-down nut that's in the process of coming off, and it was caught during inspection, but it clearly was not applied. It was not torqued properly when the cylinder was installed, and it was quite lucky that it was caught at this very early stage. Notice that the cylinder hold-down nuts never have any kind of safety mechanism. They don't have cotter pins or safety wire or anything like that, or lock washers. They don't need them. If they're properly torqued, they're not going to go anywhere, because the fastener doesn't feel the power pulses. But if they're not torqued enough, then the fastener does feel the power pulses. Here's another example that went a little bit further. This is on a Lycoming engine. It's a little hard to see, but basically the hold-down stud fractured, and the outer part of the hold-down stud, along with the nut, is gone. It just departed the premises. This was caught during an inspection, and again, this was caused by the fastener not having sufficient preload at the time the cylinder was installed. And so the stud started feeling these repetitive stress cycles, and in this case, the nut didn't back off. The stud just fractured from repetitive stress fatigue, which is what will happen. These were two fairly benign cases because the problem was caught during inspection. Here's what happens if it doesn't. This was a case that I was involved with, involving an F-model Bonanza, where the cylinder actually came completely off the engine in flight. And if you look carefully at the picture, you'll see there are 5 of the hold-down studs that fractured in fatigue. The 6th one is gone because the crankcase failed, and then the 2 through bolts, which are much larger in diameter, they're the only ones of the fasteners that didn't actually fail in fatigue, but their nuts failed in fatigue, so that the nuts came off on the big through bolts on the right side of the picture. The rest of the studs fractured in fatigue. The cylinder separated from the engine, and unfortunately, the result wasn't very pretty. The airplane, the pilot tried to make an airport, was unable to make the airport, wound up landing in an agricultural field at right angle to the it was actually a vineyard, right angles to the rows of grapes, and messed up the airplane pretty bad, and the pilot sustained very, very serious injuries. There was a big lawsuit over this one, and it was during discovery in the lawsuit, it was determined why that cylinder came off, and the cylinder came off because the mechanic who installed the cylinder used some sealant on the cylinder base flange when installing the cylinder, and he used some sealant because he thought that would minimize the chance that the cylinder base flange would start leaking oil. Well, you're not supposed to do that, and what happens is if you put sealant in there and then torque down those cylinder hold down nuts, the sealant will hold the flange and the crankcase deck slightly apart, and then during operation, as the sealant gradually disperses, the fasteners lose enough preload that they start feeling the power pulses, and eventually they fractured. So there was a huge lawsuit. Actually, Continental was hit with a very, very large damages, and they wound up rewriting all of the service manuals on these engines to put in all capital letters in a big box a very strong admonition that no sealants are ever to be used on the parting surfaces between when installing cylinders on the engine, because that's all it took. I've actually seen cases where some paint on the cylinder base flange was enough to cause the cylinder to come off because it disturbed the preload. So enough said about that. Just a couple of more points. I want to mention something called case hardening. We talked about the fact that parts tend to have their stress concentrated at the surface, and since that's where fatigue cracks normally originate, because that's the most highly stressed portion of a part, fatigue resistance of a part can often be improved by adding some preload or internal stress to the surface of the part itself to make the outer layer of the part harder and more fatigue resistant than the rest of the part. And there are several different ways of doing that. You can add internal stress to a part mechanically by rolling it in the case of sheet material, or by shot peening it in the case of castings and forgings. Connecting rods, for example, are frequently shot peened in order to harden the outer surface. Or you can do it chemically. There are a couple of processes called nitriding and carburizing. Crankshafts are typically nitrided. Camshafts are typically carburized, again, to give them additional hardness at the very outer surface of the part. Nitriding consists of, and these are both processes that are normally done on ferrous metal parts, and nitriding consists of putting the part in an oven and baking it in a nitrous oxide atmosphere for a period of 4 or 6 hours. And the nitrogen from the nitrous oxide gets absorbed in the very outer layer of the crankshaft casting, and hardens, or forging rather, and hardens the outer surface. Carburizing is a similar process, but the part is cooked in a carbon monoxide atmosphere rather than a nitrous oxide atmosphere, and it causes additional carbon to fuse with the outer surface of the metal and increase the hardness. So we can create additional surface hardness on parts chemically by nitriding and carburizing, or mechanically by rolling or shot peening. Propeller blades are another thing. They're often hardened through a rolling process. And we're taking advantage of the fact that the stress in a part is largely concentrated on the outer surface rather than on the inside. And so we can harden that outer surface and make the part more fatigue resistant. So that's pretty much all I have. Let me just kind of summarize some of the stuff we've talked about, and then I'll open it up for questions. Stress causes strain. Stress is the force that we put on metal parts. Strain is the amount that those parts deform in response to that stress. When we put metal under strain, it starts out being elastic. That is, when we take the force away, the metal will go back to its original shape. But if we put enough stress on the metal, it becomes plastic and permanently deforms. And it's that two-phase characteristic of starting out elastic and then becoming plastic that really makes metal act like metal. It have those unique characteristics that we associate with metal. Repetitive stress is what causes metal fatigue. Ferrous metal parts made of iron or steel can tolerate mild repetitive stress below the fatigue limit indefinitely. So a ferrous metal part, if operated within design limits, can have an infinitely long fatigue life, things like crankshafts. But non-ferrous parts are destined to fail from fatigue eventually. So every cylinder head will crack if it remains in operation long enough. Every crankcase will crack if it remains in service long enough. It's simply a fact of metallurgy that we have to understand and accept. Stress concentration is not uniform. It tends to be concentrated at the surface of parts, and in other places like the webs of beam structures. The surface can be strengthened through case hardening, through these various methods we just talked about. Stress is also concentrated by any geometric discontinuity, corners, holes, notches, threads, scratches, nicks, or pits. And so if we want a part to withstand repetitive stress, we need to make it as smooth as possible. We need to make the corners as rounded as possible. We need to avoid drilling holes in the part in high stress areas. Hopefully we need to avoid threading the parts. All of those things that create geometric discontinuities create stress risers where the stress is concentrated, and then if the part is going to fail in fatigue, that's where the fatigue crack will originate. Some of the components of special concern in this regard include high stress fasteners. As we've said, adequate preload is absolutely critical on high stress fasteners. If they're torqued correctly, they won't feel the repetitive stress, and so they'll last forever. Because they typically are ferrous metal parts, and if operated properly, should have an infinite fatigue life. But if they're not torqued properly, then they will feel repetitive stress, and you saw the consequences. Non-ferrous parts that are subject to high cycle repetitive stress include cylinder heads, crankcase, halves, propeller blades, propeller hubs, non-ferrous landing gear components, and for pressurized aircraft, which is kind of where we started, fuselage skins, which go through cycles every time the aircraft is pressurized, and because they're non-ferrous, will eventually develop fatigue cracks. So Tim, that's all I have, and I know we ran a little bit on the long side, but we maybe have 10 minutes to open it up for some questions.
Okay, Mike, thanks. Yeah, we've got some questions in here. Let's start out with Walt wondering, can a metal part be plated to reduce any surface imperfections and thus stress risers?
Um, well, generally speaking, and this again, I'm not a metallurgist, so my knowledge of this stuff is somewhat limited. But in general, plating actually aggravates the problem um, because, first of all, the surface. Uh, it basically creates a discontinuity at the surface of the part because you've got two different kinds of metal that are going through sort of a transition from the substrate to the plating. So plating normally will actually weaken a part, and plating, of course, is used where the major concern is corrosion, and obviously eliminating the possibility of corrosion pitting is certainly very important in order to eliminate fatigue. But the plating doesn't make the part stronger. It typically makes it weaker. And so it's a trade-off as to whether the additional corrosion resistance caused by the plating is more beneficial than the weakening is detrimental.
Darren's wondering, does stop drilling of aluminum sheet metal structure fatigue cracks really work to reduce stress concentration? Many cases you can see the crack continually propagates beyond the stop drill hole.
Well, I mean, the answer is that the stop drilling a crack, if it's done correctly, is extremely helpful because it's taking the end of the crack, which is a very, very abrupt discontinuity, and changing it into a much smoother and larger radius discontinuity. The stop drilling has to be in the right place, and the hole has to be big enough, or the crack will continue to grow through the hole. And you know that stop drilling is extremely helpful, but it does not always solve every problem. I've got some things on my airplane that were stop drilled 20 years ago and the crack stayed right where I stop drilled it, but that it doesn't always happen. There are some cases where the stress on that part are so great that even the stop drilling is not sufficient to stop the cracking. And if stop drilling doesn't get the job done, then what you have to do is cut out the bad stuff and make a real sheet metal repair.
Robert's wondering, what effect does surface polishing have on structural integrity of ferrous and non-ferrous metal?
Well, it has a lot of it's a big deal. Any surface roughness it causes stress risers, and so for parts that are under great stress, we want them to have nice smooth surfaces.
And Mark's wondering, do you recommend replacing fasteners when a cylinder is changed?
Well, the hold down nuts should never ever be reused. They should always be replaced with new. Whether the studs need to be extracted from the case and replaced, most of the time cases are not restudded when cylinders are replaced in the field unless the stud has some obvious damage to the threads. When the engine is in an engine shop for overhaul, typically those studs are replaced with new ones, and theoretically it's better to replace them, but most of the time when we change cylinders in the field. We always put new nuts on, but we typically don't replace the studs in the field. We leave that to the engine shop.
Barry's wondering if you could talk about greasing high stress fasteners so torque values provide necessary preload.
Sure. That was worded in a slightly peculiar fashion, but for example, when we install cylinders, both Lycoming and Continental are quite adamant that in order to torque the hold down nuts to the proper preload, they have to be torqued wet. In other words, the fastener needs to be slathered with lubricant before the nut is torqued into place. It turns out that torquing is really not a very good way, a very reliable way of establishing preload, because when we apply torque to a nut, the torque that we're applying to the nut is partially being used to put preload on the fastener and partially being used to overcome the friction of the threads. And because the friction of the threads is highly variable, that varies a great deal with condition of the threads, condition of the cadmium plating on the threads, the amount and type of lubricant that has been applied to the threads when we're torquing the fastener on. The amount of friction can vary quite a lot, and as a result, we can torque fasteners to the precisely specified torque and wind up with a fairly wide range of preloads, depending on how much of that torque wound up being absorbed in overcoming friction. And for years, I have been lobbying Lycoming and Continental to no avail to change their procedures for installing cylinders and other highly stressed parts, to use a different method, which is called the torque turn method, which is a method that's used in everything from big locomotives to racing cars. It's used in many industries, and it's a much more accurate way of doing things. And the torque turn method consists of torquing the fastener to a very light initial torque, which is just enough to make sure that the parts are firmly clamped together. And then, instead of torquing the fastener to a final torque value, rotating the fastener a particular number of degrees. And when you rotate the fastener a particular number of degrees, and you know the pitch of the threads, you are applying a known amount of strain to the fastener, a known amount of stretch that is independent of friction. And so it's a much more accurate way of establishing preload on these critical fasteners. But unfortunately, neither Continental nor Lycoming seems to have any interest whatsoever in changing their manuals, probably because of the standard problem that we have throughout aviation. That's if a manufacturer were to adopt a new procedure, there are a lot of plaintiff lawyers that would interpret that as an admission that the old procedure was bad, and they would be hit with a lot, or they at least be concerned about being hit with a whole lot of lawsuits saying the reason my client died was because you were using this old-fashioned torque procedure instead of the new torque turn procedure that you just published. So manufacturers tend to be very reluctant to change their procedures for fear of triggering legal liability, and so I haven't really gotten anywhere. But in any case, that's really the problem with using just the straight torque method to apply preload to these critical fasteners, is that the friction is a fairly widely variable unknown in that equation. If we're going to use we're going to continue to use the torque method, which I guess we are, we have to be very, very careful that first of all the threads are in good shape before we put these things together. So it's important to inspect the studs and so on, and to replace them if their threads are damaged, because damaged threads can cause all sorts of problems with friction. And it's really important that these parts be slathered with lubricant. Continental specifies using 50 weight oil. Lycoming specifies using 50 weight oil with the addition of some anti-friction additives. STP, I believe, is what Lycoming calls for. But the slipperier we can make those threads when we torque the fastener, the more of the torque we apply will go to applying preload to the fastener, and the less will get lost in friction. So it is super, super important that those torques be done wet, very wet, and that everything be just slathered with oil. And a lot of mechanics are reluctant to do that because it's messy. You know, when you slather all those fasteners with oil, and you got a bunch of cleanup to do afterwards. And a lot of mechanics don't really understand how critical it is, and the fact that if you don't apply lots of oil to those fasteners, then you can go through the motions of applying the proper torque, but you may not be getting the necessary preload, which is really what the object of this whole game is to preload the fastener sufficiently.
Is this only true of cylinder hold down nuts like that you slather it with the oil, or is there other fasteners also?
No, it's equally true, for example, of rod bolts, which are even more critical than cylinder hold down fasteners. Now that's kind of interesting because Lycoming generally instructs that rod bolts be tightened not to a particular torque, but to a particular stretch, where you actually are measuring the length of the bolt with a micrometer, and you tighten it until you stretch the bolt a given amount. And that is the ultimately most accurate way to do it, because again, now you're applying the exact proper preload, not indirectly through torquing, but directly through measuring the stretch. Continental does not do that. Continental specifies that its rod bolts be torque to torque, which isn't as accurate. And of course, there is no practical way to use the stretch method for torquing things like through bolts when you're putting cylinders on engines or assembling an engine, because nobody has a micrometer big enough to measure, an 8-inch long through bolt, and you couldn't get it in place even if you wanted to. So we're stuck with using torque, which isn't nearly as accurate as using stretch. But certainly when you're torquing up rod bolts on a Continental, they have to be lubricated so that you're getting the proper preload. And again, the way Lycoming does the rod bolts using a micrometer and actually torquing to a given stretch is really the ultimately most accurate way you could possibly do it. It's a much better procedure.
And Walt's wondering, is the preload on a bolt within its elastic region, or will some residual stretch remain after it is removed?
No, it has to be within the elastic envelope of the bolt. If it got to the plastic envelope, the bolt could no longer do its job.
And in the absence of stress and assuming there is no corrosion, does a metal degrade over time, i.e. long-term storage?
Not in the absence of corrosion. No, I mean corrosion is the way metal degrades. Corrosion and repetitive stress. So in the absence of those two things, no, as far as I know, there's no degradation to metal.
Okay. Michael's wondering, how can you evaluate possible fatigue in control cables?
Well, I mean the normal way you inspect control cables is, and typically control cables, if they're going to fail at a place that they're changing direction, like where they're going over a pulley or something like that, because that's where the strands of the control cable wind up having to move with respect to one another. And the normal procedure during inspection is to go to where the control cables go through changes of direction, either around pulleys or feed through blocks or whatever it is that deflect the cable, and pass a rag over the cable. And if there are any broken strands in the control cable, the ends of those broken strands will snag the rag, and you'll be able to you'll feel them very distinctly. It's often hard to see them unless you're looking with a bright light and magnification, but normally you can detect them just by passing a rag over the cable. And if there are strands coming apart in the cable, they'll snag the rag and bring it to your attention. That's the normal inspection procedure.
Okay. Francis is wondering, if a propeller is surface hardened by shot peening, can one remove stress risers by filing and not damaging the prop?
Well, I mean, obviously, the nicks are damaging the prop, and the filing is designed to mitigate the damage. It doesn't make the damage go away. It just mitigates it by increasing the radius of the discontinuity so that it doesn't concentrate the stress nearly as much. And there are specific guidelines in both the propeller manufacturers' service manuals and also in AC 43.13.1b, the Mechanic's Bible, that talk about the how deep a nick can be and still be filed out, and talk about the dimensions of how you dress a nick and how far you radius it and that sort of thing. So there's some pretty good guidance that talks about, just how much leading edge damage can be repaired by simply filing, and damage in excess of that, really the prop needs to go off and go to the prop shop, and typically the blade will get recontoured, something that a mechanic can't do in the field. That can only be done at a propeller repair station.
Okay. And John's wondering, what do doublers do when installed near a site where maybe you hang a part or something like that, where vibration is occurring and concentrated? And what consideration should be kept in mind when we load the skin as we attach appliances or install doublers that presumably increase the rigidity and transfer or concentrate vibrations elsewhere?
Well, I mean, the question is a very good question, and it's phrased in a way that pretty well answers itself. When you make when you install a doubler or you install a splice, for example, you are strengthening one part of the component, but you're moving the vulnerability elsewhere. and so you have to, sort of think things through very carefully to make sure that what you're doing is not going to make things worse. And that's a pretty complicated subject, and there is a great deal of guidance on all sorts of sheet metal repair kinds of things in AC 4313-1B, and plus a lot of airplanes have a structural repair manual that also goes into that sort of thing, that gives a lot of examples and dimensions and so forth to provide guidance as to how to do those sorts of things, using well proven acceptable methods that have been shown to hold up in practice.
Okay, Michael's
it's a pretty
wondering...
complicated subject, and the advisory circular has lots and lots of good pictures. And picture is worth 1,000 words when it comes to things like sheet metal repairs.
Okay, Michael's wondering, why does Beech advocate replacement of wing attach bolts as a function of time if properly initially torqued and there are no signs of corrosion?
Because they're boneheads. And we strongly advise our Beech clients never to allow anybody to mess with those wing attach bolts in the absence of corrosion. You do need to inspect them carefully for corrosion, but if there aren't any signs of corrosion, they really should be left alone. And the Beech guidance is just nuts, and that's not unusual. Aircraft manufacturers have a tendency to prescribe over maintaining airplanes, and a big part of what I do in my maintenance management practice is to say no to things like that. And the Beech wing bolts are a perfect example. That you're likely to do way more harm than good by messing with those things, again, in the absence of corrosion. If there's corrosion found, then of course the bolts have to come off, but otherwise they should really be left alone.
Walt's wondering, what does welding introduce any discontinuities between joined parts and aggravate fatigue cracks?
Let me preface this by saying welding is not one of my specialties. In fact, one of the things I promised my designated mechanic examiner during my A&P exam is that I would never weld on a real airplane. It's a real specialty. But having said that, yes, of course, welding introduces serious discontinuities, and in welded, for example, welded tubular construction, when they develop fatigue cracks, it almost always is at welds, because a weld is of necessity a stress riser. If the weld is done properly, it's not as much of a stress riser as if it's done improperly, but a weld is just by definition a discontinuity, and there is always a concentration of stress at any weld.
Okay, Dwayne is wondering, if you're given a torque range for a fastener, should you torque to the highest or lowest value in the range?
Well, I mean, that's a little complicated. Frequently when you're given a torque range, it's because the fastener is a drilled bolt or a castellated nut or something, and you tighten it to the low end of the range, and then you tighten it as much beyond that as necessary to get the cotter pin to line up and that sort of thing. If there's no discontinuity in there, having to worry about cotter pin alignment, and it's just simply torquing a nut onto a stud or a bolt, I would probably shoot for about the middle of the range. Typically, if there isn't something like a cotter pin to worry about, then the torque ranges tend to be kind of narrow. But if you're torquing a fastener that needs to be safetied, and there are only a certain number of discrete positions that it can be in order to be safetied, then they tend to give you a much wider torque range so that you can find a torque within that range where everything lines up properly.
Hey, we're getting close to the end here. Let's get a couple more in. Question from Harold. Are thermal stress cycles significant to metal failure, or is it more due to mechanical stresses?
I don't know enough about the thermal aspects to be able to give a good answer to that. I know that thermal stresses have been overblown in the past, things like shock cooling of cylinders and stuff, which turns out really not to be a very significant problem. But that question is actually one that I feel is a little bit above my pay grade, and I really can't answer it in any depth. I'm sorry.
Okay. Last question here from James. Will a single event such as a prop strike that stresses the metal almost to its yield point but does not cause a crack, will the fatigue life of the part be reduced?
I think the theoretical answer to that is yes. I mean, there's an expression that you often hear used by metallurgists that goes like this: metal never forgets. And that basically the fatigue life of metal is the cumulative effect of all of the stress cycles that have been applied to it, little ones, big ones, and they all ultimately add up to ultimately causing a fatigue failure. So, I think it's safe to say that a very high stress event like a prop strike, even though the part passes non-destructive testing, is likely to, ultimately have some effect on the fatigue life of what we're talking of the part. Now, that's assuming that what we're talking about is non-ferrous. If it's a ferrous metal part, and it is operated within its fatigue limit, again, it theoretically has an infinite fatigue life. And a prop strike probably will not, if the part survives NDT, it probably can be considered, again, still to be a part that has infinite fatigue life. It's non-ferrous parts that where the metal really never forgets. Ferrous parts, I guess it's safe to say, forget anything that happens to them below the fatigue limit.
Wow, great presentation, Mike. We had a number of people comment. I want to thank you for really great presentations. Really interesting, really good stuff. Thank you so much. Please take an opportunity and make closing comments.
Okay, Tim, well, just quickly, we're going to be doing a January presentation. Today's webinar was a week later than the usual first Wednesday of the month because I was in Washington, D.C. last week watching paint dry with the FAA. Sorry about that. But at any rate, first Wednesday of January, right after the New Year, doing a webinar called "Beware Fishing Expeditions," having to do with um, the possibility of mechanic grounding your airplane at a time you don't want it grounded, and how to deal with things like that. And then in February and March, I'm going to be doing a two-parter called GA and Big Data, where I will talk about some of the studies that we've done, some of the interesting results that we have come up with by studying the over 1 million flights worth of digital engine monitor data that we have been collecting on our Savvy Analysis platform for the last about 4 years. And we've got over 1 million flights from more than 7,000 different general aviation airplanes, everything ranging from RVs to Cessna 421s and everything in between. And we've been doing quite a lot of crunching of that data that we've been accumulating, and coming up with some kind of interesting stuff. So the February and March webinars, I'll be talking about our experience crunching big data with piston aircraft, and so that'll take us through March. As always, I will invite you to sign up for my free monthly newsletter. The latest issue is about to go out, so if you signed up now, you would probably get it. But it comes out once a month, and it's on all kinds of different maintenance-related stuff. And you can sign up for it either by going to savvyaviator.com and filling out the little form with your email address, or by checking the box on the post-webinar survey that Tim is going to put up as soon as I stop talking. And also invite you to check out my book Manifesto that's on Amazon.com. If you search for Mike Bush Manifesto, it'll take you right to it, and it's a small but pithy book that discusses my maintenance philosophy and the science and history that is behind that philosophy. And if you haven't read it, I think you'll find it interesting. So Tim, that's all I've got until January. I hope everybody has a great holiday season.
Thanks, Mike. Hey, I saw a Facebook notification pop up on your screen there. Would you invite people to follow you on Facebook?
To be honest with you, I don't maintain our Facebook page. One of the guys that works for me maintains a Facebook page, and I'm not even sure what's on it, except I know that sometimes he publishes some hysterically funny aviation photographs and holds caption contests and things like that. So I know there's some fun stuff that goes on there, but I'm really not personally involved with the Facebook page.
All right, fair enough. Hey, thank you so much, Mike. Wonderful presentation. A lot of people commented in about how good this was. We had a couple of people say, man, we got a much better understanding now of preload, stress, strain. Much better. Thank you, says Clifton. So good, understandable stuff. Thank you so much.
I'm glad.
And to everyone who tuned in, thank you so much. And Mike, and to everybody else still listening, thank you all so much for tuning into webinars. And have a nice holiday season. Remember, next week we actually got 2 webinars on Tuesday at noon and Wednesday normal 7 p.m. So if I don't talk to you then, have a great holiday season, and Merry Christmas and Happy New Year, everyone. And Mike, Merry Christmas, Happy New Year. We'll talk to you next year.
Okay. Good night, everybody.